Hey everyone, Mrs. Besega here with a Unit 9 review for Waves and Sound. Hey, keep in mind you should be trying this whole packet first, then checking the answer key in Drive, and finally skip to the portion of this video that you need to review. Plus, each one of these sets of standards goes along with one page of material. So the first page is going to have how to calculate and describe period and frequency, how the natural frequency results in increased amplitude through resonance, and how to calculate period and frequency based on their definition. Now we started the unit in vibrations, oscillations, and resonance because if you have a resonating object, an oscillating object that interacts with a medium, you can make waves. So step one is I need something that oscillates. That means to move back and forth around an equilibrium position. In this case, the amplitude of this oscillation would most likely be measured in degrees. Think like degrees back and forth away from the center line. Now let's calculate period and frequency. Time period is the amount of time per cycle. So I calculate this by taking total time divided by number of cycles. In this case, that's 20 seconds is the total time. And it does 40 cycles, 40 complete back and forths. One cycle would be all the way right, all the way left, and then back to neutral. So 20 divided by 40 is 0.5 seconds. From here, you can calculate frequency in one of two ways. You can calculate it by definition, knowing that frequency is number of cycles over total time. So now doing 40 over 20 seconds to get 2. Notice that cycles doesn't have a unit. So 40 has no unit, 1 over seconds. This unit is commonly called a hertz, 2 hertz, inverse seconds. It means that it goes all the way back and forth 2 times per second. Alternatively, once you get time period, the other way you could calculate frequency is using the inverse equation. Frequency and period are inverses of each other. So something that takes a long time must be going very fast, and vice versa. So 1 over 0.5 would also give us 2 hertz as the frequency. You could have also started with frequency and used the inverse equation to get period, but it's all the same equations. Pick your choice. Choose your pick. Now, we're on to the xylophone, and we're going to play on different length strips, but they're all the same metal. So which material would have the highest wave speed would be all the same. If it's all the same material, then it's all the same medium, so all the same speed. Which metal strip, longest or shortest, plays the highest frequency note when sounded? That would be the shortest, because think the short one has a small wavelength, the long one has a big wavelength. If the wavelength is small, then the frequency is high. That's because when comparing the short to long, the frequency and wavelength have an inverse relationship. So this one with a long wavelength would have a low frequency. Basically, since they all have the same speed of sound, if wavelength changes, then frequency changes to accommodate. So the highest frequency is the shortest metal strip. Finally, it talks about resonance, and anything that oscillates can have resonance, or at least anything that mechanically oscillates. Let's say a student is going swinging. If they pump their legs at any amplitude, but the correct frequency, you get resonance. So using the natural frequency of the swing, if you pump your legs at that same frequency, you get the amplitude to get larger and larger and larger. Even if you're not putting very much energy in, 100% of that energy goes into changing the amplitude. Now, E is one you don't have to super worry about until later, but we're bringing it up early. Which variable has an effect on the period of the person on the swing? We'll get into this later, but the time period of a swing depends on the length of the swing and the gravitational field that it's in. And there's a 1 over 2 pi here, if I remember this right. Or maybe there's a 2 pi on top, who knows? This is the proportion. What this equation says is as the length gets higher, it takes longer to go back and forth. So I want you to imagine, instead of this kid on a full-length swing, what if you had like just a little tiny swing, all right? It would have a smaller distance to go back and forth. It would take that distance faster. Right? Imagine if you've ever seen at a museum, the big long pendulums that are multiple stories tall. Those take a long time to go back and forth. So the length of the swing changes the period of the swing. It turns out the mass of the person doesn't super matter, and the amplitude doesn't matter either. Even if this person were to swing twice as high, that wouldn't change the time period either. But like I said, E we're going to save for later. We'll do this after this unit. So let's double check. Can we calculate the period and frequency of oscillating objects? Yes, that was this. Can we talk about resonance? Yes, that was the swing question. We calculated period and frequency based on their definitions, and bonus, we got this harmonics business. We actually also talked about how the resonance frequency is related to the size of the resonating object. We know that the longer metal strip had the lower frequency. The longer object had the bigger wavelength, so lower frequency, lower note. All right, on to wave basics. So how could students produce a longitudinal wave pulse on a slinky? Explain, including diagrams. Now, the students are the source. So let's say this is a kid, and they need to vibrate the slinky back and forth. To make compressions and rarefactions, they would need to push the slinky right and left, and the wave would also travel right and left. The source would oscillate like this. The source of the wave would vibrate, so the source shakes the slinky. And because this person is shaking right and left, and the wave speed is to the right, it makes this parallel wave. It has compressions, that's the high pressure section, so I'm going to put compression right here. It has rarefactions, that are these low pressure sections, indicated by having the medium spaced far apart. One wavelength is one complete compression and rarefaction. So imagine one complete wavelength is this. Just like with a transverse wave, whose wavelength is one complete down and back up again. So C is the wavelength, C is the period in this case. We'll talk about it later. One complete oscillation has to include both parts, an up and a down, a compression and rarefaction. So we started by making a wave. Now let's make a sound wave look transverse. Someone asked me in class, they're like, well, why don't we picture sound waves on a computer like this then? Well, because each one of these indicates the pressure. So it's not showing a transverse wave. What it is showing is that the pressure is going up and down, and longitudinal waves are transverse. So let's say we've got this wave. And in this case, it's a sound wave. Medium is air, so we know the speed of sound is 340 meters per second. and we want to calculate the period. You have some options here. You can count the total number of waves and divide by the total time. Let's do that wave first, and then I'll show you the other. So in this case, one complete wave would be every time it comes back to the same position, one complete down and up. So this is 1, 2, 3, 4, 5, 6, 7, and it's almost 7. I'm going to call this 7. I'm going to call this 7 cycles. And the total time was 0.030. So total time of 0.030 divided by 7 complete cycles, or close enough. Divide that out, and that gets us our 0.0042 seconds. Hey, this time, how did I know that a time period is measured from here to here? Well, this is because this graph has time on the x-axis. So because this graph is in seconds and is time, the peak to peak here is time period in seconds. Oh, and just fun facts so you can tell them apart. Time period is generally smaller than total time. The time period is 0.0042. It's the time for one complete down and up. And the total time, little t, was 0.03. That was the total time of motion. So they're different from each other. The other way you could do it is not quite as accurately. And the reason I say this is look at these increments. If I'm trying to measure the time period based on the x-axis, by like dropping a line here, a line here, and subtracting them, I'm not going to get very distinct numbers, or very specific. Precise, that's a good word. So in this case, I'd be estimating from here to here, and I'd probably go with 0.005 if I were estimating it, eyeballing it from the graph. So in this case, it was more accurate to count the total number of cycles and divide with total time to get the period. How to get the frequency though? There's 2 ways to do it. So if the frequency of the note played on the flute is still the inverse of time period, I should be able to do 1 over t, 1 over 0.042 to get our frequency. And that's 238 hertz. Actually, I need to revise that. I counted 7 waves in the video. There's actually 8. So let's count this here. If this is the starting point, then a wave ends when it returns to that starting point. So I marked these little purple dots on the answer key. This is 1, 2, 3, 4, 5, 6, 7, just under 8 total waves, not 7 total waves. So that changes these 2 answers. Since there are 8 waves, I would do a total time of 0.03 divided by 8 to get a period of 0.00375. And taking that period of 0.00375, 1 over that value gets a slightly higher frequency of 266. So if you were wondering why you got 8 waves and I only got 7, I messed up, but I fixed it. And we learned from our mistakes. Okay, so now, finally, we look at a simple pendulum using a motion sensor. A pendulum technically isn't a wave, right? Because a pendulum stays in place. It might disturb the air around it, but that air doesn't carry energy across the room, but we'll let it go. Okay. Let's say that we're labeling parts of this up and down movement. Equilibrium is the line in the center. The amplitude is shown by either F or G. Notice that amplitude could be equilibrium to crest or equilibrium to trough, and both count. For the crest, I put it as A. For the trough, I put it at B. And in this case, it doesn't have a wavelength. C is the time period because this axis is measured in time. If it were a distance graph, which I'm sure we'll find later, then that portion would be wavelength. Wavelength matches with position, and time matches with period. Now, let's say we double the double the amplitude of an oscillation. What happens to period, frequency, and wavelength? Nothing. If I take a flute and I play it louder, that doesn't change the note that it's being played. The wavelength of the flute is determined by the size of the flute. The speed of the wave doesn't change either. Notice that in none of the equations is amplitude affecting any other variables. The amplitude doesn't affect any other variables. Making bright light doesn't make it travel faster, or change its color, or change its wavelength. So in the same way, if you change the amplitude of a wave, it doesn't change its period, frequency, or wavelength. So let's check that we did all the things we needed to do. The source of any wave is its original thing that was vibrating. In the case of this student, it was like the student was the source. Different media for different waves. In this case, the slinky was the medium of this wave, air was the medium of the sound wave, and the pendulum was not a wave. So, okay. We talked about longitudinal waves, labeling compression, refraction, and wavelength. We labeled on a transverse wave, a transverse oscillation, the amplitude, equilibrium, crest, trough, and we'll come back to wavelength later. Promise, or probably. Now let's talk about wave speed. So we've got a sonar technician that's hanging out in this submarine. They're watching this buoy that's putting out a frequency of 6,000 hertz. So as it puts out this frequency, that frequency remains unchanged no matter how the wave refracts. So if that sound goes through air, it's 6,000. If it goes through water, it's 6,000. If the source has a frequency, that same frequency carries for all parts of the wave. So they find that the wavelength is 0.057 meters. Calculate the speed, right? I don't have distance and time, so obviously I'm using the wave equation. The wavelength is 0.057. The frequency was 6,000. And substituting that into my calculator is 342 meters per second. Now, that's a little bit higher than 340. Where might have the extra little bit come from? It could be the temperature of the air. It could be the density of the gas. It doesn't get affected by amplitude or frequency, though. Remember, the speed of any wave depends only on the medium. It doesn't depend on the frequency of the source. It doesn't depend on the amplitude, the loudness of the source. The only thing that affects the speed is the medium it's made of. Right? So now, this thing is vibrating. It's created a wave in air, and that wave will refract into water, where it changes medium. So it changes speed, but it doesn't change its frequency. So the new frequency is still 2,000. And that's because the frequency of the source is equal to the frequency of the wave, no matter how it refracts. Refraction means that it will change its speed and wavelength as frequency stays the same. So as this wave goes from air into water, the speed of the wave changes because now it's going into water. Sound travels faster in water than in air because water has particles that are closer together, and that makes it easier for the wave to be transmitted. Lambda is wavelength, so that's what we're solving for. And the frequency is still 6,000. So wavelength is 1,500 over 6,000, or 0.25 meters. Just in case you forget this, wherever you have the larger speed, you have the larger wavelength. In this case, because seawater has a faster speed of sound, you had a larger speed, a longer wavelength, whereas in water, you had a slower speed, shorter wavelength. Speed and wavelength change, frequency does not, as a wave goes from one material to the next. Next, we want a distance-time relationship. If the submarine is 2,400 meters from the sonar buoy, calculate the amount of time it takes for the sound wave to travel. You actually don't need the 6,000. That's just in there to be tricky. I'm trying to find a time, so I need to use the time equation. I'm going to use the speed of sound in water because it's like traveling through the water here. So that is 1,500 meters per second for the speed, 2,400 meters for the distance, solve for t. Sometimes people get stuck and they're like, I don't know how to solve for a variable in the denominator. No problem, not your fault you never learned this trick. This trick says that you can cross multiply. You can switch these two terms. If you switch these two terms, now I have t equals 2,400 over 1,500. Isn't that easy? If you switch these two, now I can just solve for t to get me 1.6 seconds. Ta-da! But now, let's say we change from sonar to radar. We are now using radio waves. We're going to send this signal. It has a very high frequency because electromagnetic waves just do. Calculate the wavelength of radio waves. So I'm doing lambda f. I want wavelength, so I have to use the wave equation. So I'm going to put in 3 times 10 to the 8th for the speed. I'm solving for lambda, leave that blank. And frequency is 2 times 10 to the 10th. If I divide it out, so lambda's on its own, that's 3 times 10 to the 8th over 2 times 10 to the 10th. And just be careful if you're doing this on a regular calculator and not in Desmos. 3 times 10 to the 8th, don't need any parentheses, that number looks good. But when you divide, you want to make sure the 2 times 10 to the 10th is in parentheses. That gets you the correct number. And just so you see it, what if I forgot? If I divided by 2 times 10 to the 10th, if you got a really big number, that's because it thinks you're multiplying by 10 to the 10, when we really mean to be dividing by 10 to the 10. You're off by, oh, don't worry, like a billion times a billion. It makes it very far off if you multiply those incorrectly. So, if the frequency changed, would the radio waves travel faster or slower? Neither. They won't travel faster. They travel at the same speed because they're the same medium. Same medium, it's air, so same speed of light. In this case, radio waves travel at the speed of light. So same medium, same speed of light. Cool. So how does this use the Doppler effect? So what a sonar does is a sonar sends out sound. It bounces the sound off a nearby object. So let's draw a picture. Let's say this is your submarine, submarine number 1. And it sends out a sound. And it hits a nearby object. I was going to say a polar bear, but I can't draw that, so it looks like an iceberg. An iceberg. And we want to figure out if the iceberg is moving towards or away. So what we actually need to look at is the reflection. We want to see, is the reflected wave shorter or longer than the incident wave? And for this, I'm going to draw it as shorter. Let's say that the iceberg reflects this wave, but now all these things are really close together. If the reflected wave has a shorter wavelength, that must be because the iceberg is traveling to the left as the submarine is staying stationary. You compare the reflected wave to the incident wave. If the frequency is high, they're going towards each other. If the frequency is low, they're going away from each other. So let's double check. Did we talk about the temperature of a gas? Yes. We talked about speed of sound in different materials. Yes. We calculated wavelength frequency. We calculated speed, distance, time. We didn't talk about resonating string, but I feel like we'll get there. For Doppler effect, we talked about how it has this underwater sonar question. It sends out a wave and its reflection can either be higher or lower frequency. And we'll get back to Doppler. I know we get back to Doppler later. Oh, we get back to Doppler now. So it says draw short lines that show the wavelength and the sound waves in front of the car. So in front of the car is person B. These are the wavelengths. Look how tiny they are. B has a short wavelength. Because the car is traveling to the right, the wavelengths get squished together. And if the wavelengths are squished together, then the wavelength is small, so the frequency is big. B hears the highest frequency of sound from the car because its waves are smaller, so it has a larger frequency. Now, a stationary police officer shoots a radar at the car, that's radio wave frequencies, and observes the reflection. This time, it has a lower frequency. This means these are moving apart from each other. This must be the car moving away from the police officer based on the choices. If the frequency is lower, they're moving apart. If the frequency were higher, then they'd be moving together, like B. So now we have, I don't know, a crazy motorcycle gang. Maybe they're like doing a performance. Who knows? So we have 4 motorcycles all traveling at 10 meters per second to the right. They're all traveling 10 meters per second. And the police car is traveling 10 meters per second to the right. Let's look at the direction these are traveling. We'll throw in some numbers here. So A is traveling to the right. The police car is traveling to the right. B is traveling left. C is traveling left. And D is traveling right. Which motorcycle rider hears the highest frequency of this source? So this is your source. Well, if they're moving together, they hear higher frequencies. So C is going towards here, but none of the other ones. C must have the highest frequency because it's the only one that is getting a shorter and shorter distance between itself and the police officer. It's not like the distance matters. What matters is the direction of motion, towards or away from each other. Since these are the two going towards each other, they have the same frequency. They have the highest frequency. The lowest frequency would be ones that are moving apart. So B is moving apart from the siren. So B would have the lowest frequency. And that leaves both A and D having the same frequency as the siren. Since A, the siren, and D are all traveling to the right at 10 meters per second, none of them is moving relative to each other. And remember, the Doppler effect is an apparent change in frequency due to the relative motion of the source and the observer. A and D don't have relative motion, so they don't get a change in frequency, so they don't have a Doppler effect. It works for all types of waves, including water, sound, and light. This would be a sound wave. These would be a sound wave. The radar would be a light wave, right? And then Paul Hewitt did the water wave in class when he was talking about like the bug floating on the surface going bloop, bloop, bloop. Cute. So on wave behaviors, haha, I told you we would come back to transverse waves, right? For wave behaviors, we want to see if something will be constructive or destructive interference. At point A, I have one amplitude going up, it's actually 2 boxes up, and an amplitude going down, 5 boxes down. Hey, A would have destructive interference because the waves are on opposite side of the line from each other. The wave going up would cancel the wave going down, so you get destructive. Not perfectly destructive, right? Because think this would be +2 and -5. You'd have an amplitude of -3. But destructive because it's making the amplitude smaller than it was before. At D, you have constructive interference. This amplitude is -2. This amplitude, hey, is also -2. So D would have an amplitude of -4. 2 waves on the same side of each other have a larger amplitude. The amplitude would be 4 if you added these together. Next, here's that transverse wave I was talking about. This is a transverse wave with the medium of bridge. All right, how is this a transverse wave? Well, notice that the wave is traveling, I guess, to the right, right? The wave's traveling to the right, but the bridge itself is moving up and down. They're moving perpendicular to each other. That's why I'm saying it's transverse. Plus, if it were longitudinal, you really couldn't see the pressure traveling through the bridge. So you wouldn't be able to see a longitudinal wave in the same way. Now let's talk wave behaviors. Wave travels down the bridge, hits the upright, bounces back. That's reflection. Now I have 2 waves in the same medium. I have the original incident wave and its reflection. And if they're in sync with each other, we can make them interfere to either add amplitude or subtract. So on the diagram right, label the nodes and antinodes. The node is right in the center. It's a little hard to see. It's more clear in the GIF. Our nodes and antinodes are right here. On the printed copy, it's harder to see than on the other one. Sorry about that. You have nodes at the end because this behaves like a string. Node in the middle. And then you have the antinodes where the amplitude is moving quite a bit. Destructive interference is where the node is. If you had a car on the bridge, this car wouldn't even be moving, and you would just see the ground moving around it. That'd be so weird. This has to be the second harmonic. I'll draw it out for you. But if I were to look at this exactly from the side, I'd see the bridge looks like this. Oh, let's draw it from over here so you can see it. There we go. Sorry about that. And right now, the bridge looks like this. In another second or so, the bridge would now be like this. Each portion of the bridge vibrates up and down as the wave travels right and left. This is an example of resonance because on this day, the frequency of the wind matched one of the natural frequencies of this bridge. Now, all natural frequencies cause resonance, and materials can have more than one resonance or natural frequency. So this is an example of a resonance phenomenon because you put in the right frequency and the amplitude got big. So big that it increased the amplitude until the bridge collapsed. So, did we do the things? We talked about reflection. I talked about refraction when we talked about the wave traveling from sound wave traveling from air into water. We talked about interference. a little note on diffraction. We'll head back to that later. Then, interference. We talked about constructive interference occurring at antinodes and destructive at the nodes. And we can find where nodes and antinodes are. Easy peasy. The last 2 pages are all the same standards. We're talking about having resonance. So please be able to draw standing waves, including for string instruments like the first harmonic. All right. Label the nodes, label the antinodes. And it looks like the third harmonic. So when I'm doing this to make it nice and neat, split your harmonics up into 3. So I split my wave up. Then I make one sine wave. It hits the edge, it reflects back. We have nodes on the end for all string instruments, antinodes in the middle, and one wavelength is 2 complete antinodes because it's one complete down and up of your original wave. So be able to draw and label. Be able to calculate. The wavelength of the first harmonic is 2L over N, where N equals 1. It's N of the first harmonic. So 2 times 60 centimeters over 1. Oh, that's totally math I can do in my head. That is 1.2 meters. Make sure to convert centimeters to meters, my friends. Frequency. There are 3 potential frequency equations, but you only have enough information for one of them. The wave equation. You take the speed of the transverse wave on the string, that's your 516 meters per second. The wavelength is 1.2, and divide them out. Frequency is 516 over 1.2, or 430 hertz. Sorry, musicians, that's like just not a pleasant note. It's like not quite an A. All right, so now let's say I have my wavelength for the first frequency, that's 1.2. The second frequency is 430. And the speed of all of these is 516 because it's all the same medium, all the same speed. To get the other frequencies, we can do multiples. If the first frequency is 430, then the second frequency would be 860. The third frequency, get the picture? They're multiples. You keep taking the original frequency and multiplying them up. Make sure not to make the mistake where you're like, oh, it's 430 times 2, it's 860 times 2, it's 1290 times 2. That's just not true. Take your original frequency and multiply them up. For wavelengths, I could do something similar. I could do 2L over 2, so that's 2 times 0.6 over 2. I could do 2 times 0.6 over 3, repeating the 2L over N equation repeatedly. But alternatively, you could across each row do wavelength times frequency equals speed. Alternatively, across every row, wavelength times frequency should equal speed. So I could do 516 divided by 720, and that would get me the correct answer. Now, let's double check. Are we doing the thing? Wavelengths decreasing? Check. Frequencies increasing? Check. Wave speed all staying the same? Yes. Across every row is consistent? Check that on your own time. But those are my 4 patterns I'm looking for. So now, I want you to imagine I'm playing the ukulele, the little green instrument that I play during class sometimes. If I'm playing that instrument, a string instrument, and I tighten the tension, that increases the velocity of the velocity of the transverse wave on the string. But the wavelength doesn't change, because the wavelength depends on the length of the string, and you didn't change that. Wavelength depended on L, and you didn't change L. It's still the same string. So picture, you're tightening the string of a ukulele. You tighten the string, the speed goes up, but it's still the same length string. Since the speed has increased, the frequency increases. But the wavelength remains the same because it's the same size string. If I change the size of the string, however, so now I put my finger down, wavelength decreases because if length of the instrument is smaller, the wavelength that fits on it is also smaller. If it's still the same string, then it's still the same speed. But you hear a higher note because since wavelength is smaller, the frequency is higher for the same speed. So the medium remains the same, but you made a shorter wave in that medium, so now the frequency is higher. The last one, tube resonance. Draw the standing wave for the first harmonic. Guys, I literally did this in class. I took the frequency generator, and I think the frequency I had was like, I don't know, 122 hertz or something. We take the speaker, and it makes this resonance pattern. We know it has antinodes on the end because think like the sound is very loud near the speaker and it's very loud near the end. If you put your hand in front of this tube, you can literally feel it shaking the air. So the length of the tube is 0.34 meters. Calculate the wavelength of the first harmonic. Let's use that wavelength equation. That's 2L over N. That's 2 times 0.34 over 1, or 0.68 meters. You get a point for the equation and a point for substitution. The first resonance frequency, so N equals 1, is 520. So if I do speed is wavelength times frequency, that's 0.68 times 520 is 353.6 meters per second. This speed is higher than predicted. It's higher than 340. This could be because the air is hot. This could be because, I don't know, maybe I let a helium balloon go in the room. Who knows, right? The speed of sound depends on the gas that it goes through. So if it's not quite air, right, then its speed would change. Most likely this has to do with temperature and humidity. If we change those factors of the medium, you change the speed. So the frequency is slowly increased until the next harmonic is heard. Calculate the second frequency where resonance occurs. Well, that's easy peasy. We know if the first frequency is 520, then the second frequency would be twice as big. This N times F1 equation means the second frequency is twice as big as the fundamental frequency. Remember, the first frequency has a special name called the fundamental. Right? It's the main note that you hear. It tends to be the largest in amplitude. So my next frequency up is 1040 hertz. I'd get a point for the equation and a point for the substitution. To make the second harmonic, I'm going to split my wave up so that I have two half waves, one on each end, and two half antinodes on each end, and a whole one in the middle. It's actually only one wave, right? Because it's one complete down and up. And we put the little reflection in. There we go. I have antinodes on each end because that's where the pressure is big, an antinode in the middle, and two little nodes. You would literally have to worry about this in a tunnel if you were designing one for like trains or cars or something to drive through, because then if you had that big resonance pattern and it's doing something like hitting a car or shaking the tube so much the concrete collapses, hey, that would be a bad day. So back to this pattern again. We know frequencies are multiples of each other, and we did one of these already. The next frequencies up, let's just math it correctly for us. I guess you could also do this as just adding. So 1560, add it one more time. 2080. We know the first wavelength was 0.68. Now we're going to do that 2L over n equation repeatedly. So that's 2L over 2 is 0.34. How about we do 2L over 3 is 0.22. Let's call it 0.23. We'll round that correctly. 2L over 4. And just to double check, wavelengths decreasing, frequencies increasing. Beautiful. All right, everyone. So best of luck to you. We didn't ever head back towards diffraction on here because we'll hit that in the light unit, but we did hit all of the other objectives for this unit. So best of luck. See you later.